All right, ladies and gentlemen, while this is popping up, I hope we're all having a good day today. I am unfortunately at the dentist's office getting some work done, so hopefully you're having a better day than I am. Okay, so we're going to jump into the next chapter here. This next chapter is section 7.1. Really, all of chapter 7 is about exponential functions, and their inverses too. We're actually going to talk about logarithms this chapter. But yeah, so section 7.1 is just kind of like a basic application of exponential functions and just like a little bit about them and, talking about their parent too. Okay, so let's get to it. Again, remember, as always, when we do these video notes, try to make sure you write everything down that I say to, and just to, kind of take this, take this seriously. Make sure you understand all this stuff because this is kind of like the base for this whole chapter. All right, so let's talk about the basics of an exponential function. So we've got this application here. This is the application that the book gives. So don't, don't read too much into this. It's just a cool example of this thing's called Moore's law. It's basically a rule that's used in computer industry. States that number of transistors per integrated circuit doubles every year. I've often heard this about technology too, that like technology will double every single year that you have it. Like the technology that we have now will be doubled by the time we come around to this time next year. Just like the things that they can do, and the different things that we can do with our technology. But that's not exactly what this is about. But think about that thing. Think about the idea of something doubling every year. Like, for example, take this table. A lot of times in the past chapter, we looked at tables and said, okay, what's the pattern in the y values? I mean, look at the x values, just going up by 1, 2, some. Oh yeah, it's all going up by 1. Nothing's going up by 2. I don't know what I'm talking about. But take a look at the y values here for this table. It's going up by 60, then it's going up by 120, and then it's going up by 240, and then it's going up by 480, and so on and so on. So it's not going up really at a steady rate. If I try to find the differences within the differences, nothing would happen. But what I do see here is that it's actually multiplying. It's actually multiplying by a certain amount. Every time I take the y values, 60 to 120 to 240 to 480 it's actually doubling. So it's not actually adding, it's actually multiplying each time. This is the case where it's doubling, right? So if I'm having this is actually not a polynomial function anymore. It's actually an exponential function. It will actually grow a little bit quicker. Growth doubles every year can be modeled by using a function with a variable as an exponent. Or variable as an exponent, excuse me. This function is known as an exponential function. This is the parent exponential function. Let me get a marker here. I would write down this. The parent exponential function is f of x is equal to b to the x, where b is the base and a constant. Sorry, b is a base, which is a constant, and the exponent is x is the independent variable. I would write that down. That's our definition. That's our exponential function. It seems weird to have a parent with 2 variables in it, but the base is just a constant. So if I'm looking at like 2 to the x, that's something, that's an x. That's something doubling every time. Now, we'll often use 2 to the x to transform, to do all that fun stuff, because that's the most basic one that we can get. I actually think I do have another little image of it down here. Yeah, there we go. Because I was going to talk about how this has to be greater than or equal, or is it not greater than or equal to, but greater than 0. If the base was equal to 0, 0 to any power would be 0. So therefore, it wouldn't work out very well. It'd just be a straight line. And b can't be 1 either. Well, why not? Well, 1 to the x would just be, well, think about it. 1 to the first would be 1. 1 to the second would be 1. 1 to the third would be 1. 1 to the fourth would be 1. It's not doubling every time, So it's not technically an exponential function. It's not tripling. It's not quadrupling every time. It's not technically an exponential function. It's more like a literal straight line. For x is 1, y is 1. For x is 2, y is 1. For x is 3, y is 1. So it's actually a vertical line right there. Oh, no. I'm sorry. A horizontal line. I had that backwards. It's actually a horizontal line. No matter what the x value, the y value is consistently 1. Horizontal line. Said that wrong. All right, so this is our if you want, you could write that down too. But it's just interesting to note that we're only going to have positive numbers here. We're assuming that b is positive. B is negative. well, then it's just reflection. But we're assuming that we have positive numbers, non-zero positive numbers, and we have b is just not 1. If it was 1, then it would just be a flat line. No good. All right. That's what I thought. Okay, let's talk about this graph here. Hopefully I don't see anything past that. Okay, good. Take a look at this table here. This is 2 to the x. We could call this the parent 2 just because it's the most basic one that we can get. F of x is equal to 2 to the x. Take a look at the table that we have here. If I take 2 to the negative 2 power, that's actually, well, 2 to the negative 2, that would be 2 to the negative 2 power. That's a 2. That's a 2. It would be 1 over 2 to the second power, 1/4. 2 to the negative 1, 1 over 2 to the first power, 1/2. 2 to the 0 is 1, anything to the 0 is 1. 2 to the first is 2, 2 to the second is 4, 2 to the third is 8, and so on and so on. Notice how, like, if I kept this going, 2 to the fourth would be 16, 2 to the fifth would be 32. It's increasing at a rapid rate. I only increase by 1/4, then 1/2, then 1, then 2, then 4. Then that escalates pretty quickly, doesn't it? So that's what the idea of an exponential function is, right? It's increasing at a very rapid rate, right? Okay. So let's think about the domain and range of this function, because it's always good to identify what the domain and range. Now, it doesn't matter what, I could plug any x value in. I could have x values that are negative. I could have x values that are positive. I could have x values that are 0. I could have x values that are decimals. So the domain is all real numbers, but the range, take a look here. If I keep getting smaller and smaller with my x values, is it ever going to go below 0? Like, think about it. Can I make the x value small enough that it'll go below 0? Like 2 to the negative 1,000th, right? 2 to the negative 1,000th. What would happen there? Well, isn't that just 2 to the 1 over 2 to the 1,000th, right? Did that go below 0? Is that below 0? No, that's not below 0. That's still above 0. Very slimly above 0 because it's just a really small number, right? Really, really small decimal. So take a look at what's happening here. The range is actually all y such that y is greater than 0. Not equal to. Notice that there's not an or equal to here. It's just y is greater than 0. Okay, it's going to get closer and closer and closer and closer to 0, but it's never actually going to touch 0. Yeah, that idea is known as what's called an asymptote. An asymptote. I'm pronouncing the P, but you don't really actually pronounce it. It's an asymptote. Go ahead and write that down. An asymptote is a line that a graphed function approaches as the value of x gets very large or very small. We're going to deal with asymptotes in both Chapter 7 and Chapter 8. So it's a good idea to get a hand on them now. Basically, the idea of an asymptote is something that's going to get closer and closer and closer and closer and closer and closer to reach, but it's never actually going to get there. Yeah. Like, say, for example, if you were going to get, you were going to go meet somebody. You were standing across the hall from somebody, and you said, I am going to take half the distance every step I take, right? Well, think about it. Here's you. Here's your friend. It's really awkward because you're going to walk toward them half the distance. Well, that's not half, but anyway, you're half the distance there, and then walk half the distance there, and then walk half the distance there, and then walk half of that distance there, and then walk half of that distance there, and then walk half of that distance there. Are you ever actually going to reach your friend? I mean, yeah, you will physically get closer and closer, but will you ever be at that spot that they were at? No, because you're always taking it half and 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 half. And if you multiply something by half, you're never going to get 0. Unless you started with 0, which we didn't. We started with something bigger. So the idea is you're going to get closer and closer and closer and closer and closer and closer, but you're never actually going to get there. That's the idea of having an asymptote. All right. Now we got to talk about exponential growth and exponential decay. These are two specific types of exponential functions that we'll use a lot in word problems. Basically this. Exponential growth is where b is bigger than 1. Exponential decay is when b is in between 0 and 1. Basically a fraction, right? Exponential growth is b is greater than 1. Exponential decay is when b is between 0 and 1. Basically, b is a decimal, or b is a fraction between 0 and 1. If b is bigger than 1, 1.5, 2.5, 3.5, whatever, 1 million, it's going to be exponential growth. If exponential decay, it would be 0.5 or 0.75 or 0.9 or 0.25, or not 1.5, that's exponential growth. If it's bigger than 1, it's an exponential growth. If it's less than 1, it's exponential decay. Yeah. Let's identify some of those. All right, well, these should be very easy. Exponential growth or decay? Well, is this between 0 and 1, or is this bigger than 1? It's between 0 and 1. So we would call this an exponential decay. Now, when it says to graph, I am definitely okay with you using your graphing calculator. So let's go there. Oop, looks like I had a regression in. Let's get this junk out of there. Oh, let's get my plot off too. Okay. I am definitely okay with you using your calculator. So let's go down here and let's plug this in. 10 times 3/4 to the x. I'm going to zoom 6 because I don't know where my calculator's been last. You should do that too. Notice how it's going down? It's exponential decay. Going down, exponential decay. Decreasing, 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 decreasing. Notice how the asymptote is still there, right? It's going to get closer and closer and closer to 0, but never reach it. Same thing here. Okay. Bigger than 1. Growth, right? Exponential growth. Let's see what that looks like on the graph. Here is my, okay, it's going to be 100. Let me insert a 0. Insert a 0. And 1.05. 1.0, oops, going to insert 1.05 to the x. Graph that. Uh-oh, I'm not seeing anything. What does that mean? It's probably, oh, look, 100. That must mean something. I'm going to zoom. Ooh, let's try zoom fitting. That might help. Zoom fit. See if that does something good. Okay. I don't really love that graph, but basically, if I were to graph this, it would look like this. Whoop. Yeah. Shouldn't really curve upward down there, but forgive me. But it should look like that. You see an exponential growth. Yeah. It's in slowly increasing, and then it was really quick. Right? That's exponential growth. All right. Now, for these word problems that we're going to have, when I talk about exponential growth and decay, and I want to model it with an equation, this is the equation. You're definitely going to need to know this. Yes. Okay, so it's A of t. So pause here and write that down. A of t, where A of t is your final amount. That whole thing is your final amount. A little a is your initial amount. And then I have 1 plus or minus r. R is the rate of increase as a decimal. So say I had a 30% increase, it would be 0.3. If I've got a 5% decrease, it would be a 0.05. T is the number of time periods. So say for number of years or number of days or number of months or number that you'll get from the context of the problem. Now, it's interesting to point out here that I have a plus or minus. Why? Because this models both growth and decay. Think about it. This is the base of my exponent. So if I want a growth, I want to do something bigger than 1. 1 plus r. If I want a decay, I want to have something less than 1. 1 minus that rate of decay. So, oh, that's just what I talked about. Get out of here. Let's do an example. All right, Clara invests $5,000 in an account that pays 6.25% interest per year. After how many years will her investment be worth $10,000? Okay, so let's first off write our equation. Well, what was our equation? Well, it was A of t is equal to little a times 1 plus or minus r to the t, right? That's our function. So now our initial amount, A of t, little a is our initial amount. Final amount, yeah, let's just write our function first because I don't want to confuse us with our 10,000 there. A of t is equal to our initial amount, $5,000 times 1, and now it's plus or minus. Is she going to gain money or is she going to lose money? Hopefully she's not going to lose money. And she's investing it, so she's going to gain money that pays 6.25% interest. So I'm going to plus 0.0625. Notice that I put that as that decimal as that percent as a decimal raised to the t power. So it's 1.0625. So there's our function. A of t is equal to, I'll just get $5,000 times 1.0625 raised to the t power. That's our function. Now, here's what I want to do. After how many years will the investment be worth $10,000? Now, don't write this down, but go with me here. Don't write this down, but go with me. I want to know when this final amount is going to be equal to 10,000, right? 1.0625 to the t power. Okay, so if I divide by, normally I would say to solve for something with a variable, I want to move everything off to the other side. So I would divide 10,000 divided by 5,000. I don't know why I just didn't do that. Is equal to 1.0625 raised to the t power. So that's just 2 is equal to 1.0625 to the t power. How do I solve that equation? Do I square or root it? No. Do I take, ladies and gentlemen, we have an issue here. We don't know how to solve this equation. Right? We don't know how to undo an exponent. We kind of do, but that's when the x is down here. If that was squared, I'd square root the opposite side if the t was down here, but the t is up there. So how the heck do you solve for an exponent? Spoiler alert, a logarithm. Now, we aren't going to touch logarithm. That's an ITHM. We aren't going to touch logarithms right now, but I'm just kind of letting you know we would solve this by using a logarithm, right? But we're not going to touch that right now. We're just going to do something else. Okay, we're not ready for that yet. Hold your horses. Here's what we can do. We can graph it. So let's go into our graphing calculators. Let's go into y equals. And here's what we're going to do. We're going to plug into our y1, our function, 5,000 times 1.0625 raised to the x power. And then we're going to put in our second y, our 10,000. We're going to treat this as like a system of equations. Right? We're going to say this is our y1 and this is our y2, and we're going to see what the intersection point is. Now, I'm going to zoom 6 this. I'm not going to see anything, but I want to get it back to my standard window before I do anything else. Let it run. Okay. Zoom, and now let's see if zoom fit works any better. Let's see. Okay, here's my exponential. Oh, do I see my intersection point? Dude, it's right there. Bummer. Zoom out. Zoom 3, enter. So here's my exponential coming across. Very good. Here's my 10,000. Okay, so second, calculate the intersection point. First curve, enter. Second curve, enter. Second, last guess. And there we have it. After 11.43 years. Yeah. After 11.43 years, we would get up to $10,000. Yeah. Could you have also seen that in the table? Why? Of course you could, right? How much is it going to, when is it going to go 10 years? I'm sorry, not 10 years. When is it going to go past $10,000? Looks like right there, right in between here, right? In the 12th year, or you can actually figure out the exact amount just by doing this guy. Yep. Last problem here. A city's population, which was initially 15,500, has been dropping 3% a year. Write an exponential function and graph the function. Use the graph to predict when the population will drop below 8,000. And then what will the population be in 10 years? Kind of complicated problem. Let's start off by writing our function. Okay, so A of t is equal to, now we've got little a, initial amount, 15,500 people, times 1. Now, is my population going to grow or decrease? It's going to decrease. 1 minus 0.3 raised to the t power. Usually our exponent is our variable. So that's going to be, here's my function, 15,500 times 0.97. 1 minus 0.03 is 0.97 to the t power. Okay, so there's my function, right? Let's put that in our calculator. Let's go to my y equals, and let's remove our old guy and say 15,500. Something's wrong there. Whoop. You didn't see that, did you? Okay. 15,500 people times 0.97. That's embarrassing. I hope when you're watching this, it's still before 8 o'clock. 0.97 raised to the x power. All right. Now, I want to know, so I'm going to graph this and use the graph to predict when the population will drop below 8,000 years. So I want to know 8,000, right? I'm going to zoom 6 this, put it back to my standard window, and then I'm going to zoom fit it and see what happens. Let it run. It's thinking. And now we go zoom fit. There's our decay. Slowly creeping along. And here's our 8,000 line. Okay, now I'm going to zoom out. Zoom. 3. Enter. Here's our decay. Let's hope our 8,000 is crossing. Ooh, I think it's going to cross. Yay. Okay, so we're going to second calculate the intersection point. Enter, enter, enter. And there it is. Okay. How long is it going to take to go below 8,000? For more than 21.7 years. Yeah, 21.7 years, it will drop below 8,000. So what will the population be in 10 years? Well, this should be on my screen. I'm going to second calculate a value, a t value of 10. There it is. What will the population be in 10 years? Well, the population will be 11,430.074 people. Yeah. Hopefully you're not that 0.074 of a person. All right. So that's exponential growth and decay. We're going to work with a lot of word problems with this stuff. So, get a good base of this and we'll be good. I hope everybody's having a good day. Probably a better day than I'm having. Ooh, dentist. Okay, bye. Have a great day. And I'll see you later.